Sorry about that. Okay. So let's talk about what is going on with our bell work. We're actually going to start this off with a bit of a chemistry lesson, which is fun. So looking at this scenario here, we've got this ice bath of water sitting in a room, taking it, placing it into this warm environment. When we take a bucket of ice, put it into a warm room, what do we expect to kind of have happen? It's going to melt, and then we're going to see that that temperature kind of goes to match the room. Now, what is really, really interesting is that if you were to, at any point while the ice is melting, stick a thermometer into that mixture of ice and water, you are always going to get the same temperature measurement. All right. Now, what is the temperature of water when it either is melting from ice into its liquid or when it is freezing from water into its solid? It's going to start out at 32 degrees. So this is like the melting point, which is really the same as the freezing point, which for water, 32 degrees Fahrenheit or 0 degrees Celsius. Celsius with water is much nicer. What we see is this phenomenon where for the first little bit of heating up this kind of this ice bath, the ice will melt, but the temperature does not change. There are two different kind of measurements of what is changing when we are supplying energy into a system. There is heat, which we will commonly refer to in chemistry as the enthalpy of the system. This is like what you are actually measuring when you are taking the temperature. And what we notice here is that the enthalpy doesn't change. All right, so there isn't any kind of heating up going on. Enthalpy in the system stays constant. What is changing, though? If it's not the temperature, it's the amount of water in the bucket compared to the amount of ice. And so what's actually going on, what we are increasing is not the heat, but, and I like to say this because it makes it sound kind of like a supervillain, we're increasing the amount of chaos inside of the system. We think about like an ice cube and we think about like the structure of an ice cube. How easy is it for us to kind of move the atoms of that ice cube around? How easy is it for us to like shift around that structure? It's really hard. In fact, it's really hard to do that with any solid. We could imagine taking like this table and having a really, really hard time moving the table's atoms around in any kind of meaningful way. Whereas with water, how easy is it for me to jumble up and mix up the structure, the formation of the water molecules? It's very, very easy. You can slosh up water all around and the molecules will be in slightly different configurations. That's very, very easy. So that's what we're talking about with chaos, is like how mobile the molecules are, how crazy things are allowed to get. The other word, the more scientific word for it, is rather than increasing the enthalpy of our system, what are we increasing? Does anyone know? Disorder, which has another cool word that starts with E. Sounds kind of like enthalpy. It's probably actually the one you've heard of. Entropy. We are increasing the entropy of the system without increasing the heat. So this is increasing entropy. All right. Eventually, we run out of ice. And as soon as we run out of ice, our system is as chaotic as it's going to be, at least for the time being. For now, it's going to be about as chaotic as it's going to be. And so what do we see once we hit that kind of point where there is no more entropy to be added? All of our solid is now liquid, and our liquid doesn't really want to, is not being very motivated to become like gas. Well, we're going to see now that we can't increase entropy, we will instead see an increase in heat. All right, so for the first hour where this ice bath is melting, the temperature isn't changing because what's changing is the chaos of the system. And then as soon as that hour elapses, all of the ice is melted. Now there's no more chaos to be introduced. for now. Now we'll actually start to see an increase in the temperature. So we'll see an increase in heat or enthalpy. All right, how long will that increase go? Well, it will go until the boiling point of this particular substance. What is the boiling point of water? Does anyone know off the top of their heads? 212 Fahrenheit. Again, if we were working with Celsius, this would be nice. This would just be 100 degrees Celsius, which is just nice and easy. 0 is freezing point, 100 is boiling point for water. So this is the boiling point. I think it's generally just called the boiling point. I guess maybe you could call it like the condensation point, but boiling point is more often than not what you'll see. Yeah, right. Yes, sorry about that. So we end up with our boiling point, and then again we see something very, very similar where now our water is going to again want to become very, very chaotic. Our water molecules that are relatively mobile are now going to separate further apart. They're going to boil. They're going to get water vapor in the form of a gas. But until all of that water has boiled, just like before, we are no longer going to be increasing the enthalpy of the system. We go back to increasing the entropy. We make that water bath that is now, boiling away, that is going to be becoming very chaotic, but not becoming very warm. Right? Now, our room at 72 degrees is not nearly hot enough that we're going to see this kind of second plateau here for our function. But really, what we have is like a piecewise function here, where for the first hour, we are behaving like a constant function. Our stuff isn't changing. And then for the second hour is where we actually start to see, second hour and on, or after the first hour, is where we really start to see this kind of heating up process take off. So this is kind of what I was saying of when I say 4 hours, how long have I actually been heating up? I've only really been heating up for 3. Newton's law of cooling has only really been in effect for those 3 hours. Okay, so we can incorporate that into our equation. The other way that you could do it is you could just make a mental note and say, oh, when it says 4, I'm just going to plug in one value less. That's going to have a couple of complications when we reach the very end. So I'm going to alter my equation to make it so that when I plug in 4, it's like I'm plugging in 3. What would I have to do to my, well, let's set up our generic equation here first. So this is T of T equal to A times E to the R. And then normally I would have T here, but what do I need to do to my T to adjust for that hour where I didn't do anything? So plus 1 would be if I plugged in 4, I would be 5. So I want to instead, other direction, subtract 1 off of the amount of time that I'm plugging in. We're going to do like T minus 1 here plus this T sub s. All right. What is T sub s? This is 72 degrees. And then what is our initial temperature here? It's kind of like T sub 0, but really we kind of want to think about this as like T of 1, which is like where we actually begin. Kind of like yesterday, how we began when the old model was at 2 hours. Now we're kind of beginning after an hour has passed, we start heating up. Either way, it's the same as T sub 0. What is the initial temperature of our just pure water? This is going to be 32 degrees. Very, very nice. And so our value of A here is going to be what? Negative 40. Very good. So yeah, so why is our A, so this is a really good question here. Why is our A negative here? And what would cause the A to instead be positive? Okay, so this is, in this case, our A is negative because the temperature of our object is less than the temperature of the surrounding environment. Imagine instead a situation in which I take like a boiling pot of water and place it in a cool room. Well, first, all of the water vapor is going to need to condense. So we'll again still have that kind of blanket period where we stop our phase change. And then we'll start cooling down. And the thing to note there is that that difference will instead be positive. T of 0 minus T sub s will be positive. So it's possible to have either, and you'll get positive coefficients when you have a hot object in a cold room, and you'll get negative coefficients when you have a cold object in a hot room. Very good question. All right. So we can go ahead and start kind of filling out what our formula is going to look like here. T of t is going to be, we said A was negative 40. E to the r times t minus 1. Again, just minus 1 because whatever I plug in, I want to account for that hour that I spent spinning my wheels, and as far as enthalpy is concerned, doing nothing, and then plus 72. So what am I missing here for my formula? What am I going to start off needing to find? I'm going to start off needing to find this value of r here. How did I find r yesterday? What did we end up doing? Say again? So that gives us the value of a. That's how we found that a value there. How do we find, what do I need to do? This is where we're going to start needing to like solve stuff. How do I solve for r? Yeah, so we're given a point here. We need to be given a point, a combination of input and output. Our point is 440. Now, you might have used 3 comma 40, which is fine if your equation doesn't take into account the fact that we spent an hour doing nothing. My equation does take that into account because I have that minus 1 there in my exponent. All right, so I'm automatically reducing my input by 1 when I plug it into my function. So I'm perfectly happy to plug in 4. In fact, I need to plug in 4. Regardless, what we do when we get this, we should end up with 40 equal to negative 40 e to the 3r plus 72. Regardless of how you did it, you should end up with that 3r. That 3 represents the number of hours that we have spent heating up. All right, I spent 4 hours in this room. 3 of those I've spent heating up. And so what do I have to do here to solve for r? Yeah, we have to get e to the power by itself. So subtracting 72 from both sides, dividing by negative 40. I get negative 32 over negative 40, which coincidentally simplifies to be very nice. What does that end up being? 4 over 5 is equal to e to the 3r. And then how could I get the r out? I like rewriting it as a logarithm. So this is going to be the ln of 4 over 5 equals 3r. And then solving for r, dividing both sides by 3, I get that r should be the ln of 4/5 divided by 3. Now, Haddon here had a really good question, which is, can I do anything with this divided by 3? And the answer is yes. And we kind of had this cool realization that while I can't divide that 3 into the contents of my logarithm, I could think of this as being like multiplied by 1/3. And so another way that I could definitely write this is the ln of the cube root of 4 over 5. And then that would work. You don't need to do that. I personally left my stuff like this, but just as far as like how we could incorporate that 1/3 in, we could use the power rule kind of going in the opposite direction to rewrite this as like 4/5 to the 1/3, and then that's just the cube root of 4/5. But either way is fine, whichever way you prefer. But very, very importantly noting, we can't actually do out this division as it stands. We either need to just leave that alone or use the power rule to bring it in, and either way is fine. So when we do this, I, for my equation, get that t of t is equal to negative 40 e to the ln of 4/5 over 3 times t minus 1, again, that adjusted value of t, plus 72. All right, and what am I actually looking for here? This is all the setup. This is to get our formula, but what am I actually trying to use our formula to figure out? Trying to use it to figure out the time at which what? Perfect. So 52 should be equal to negative 40 e to the ln of 4/5 over 3 times t minus 1 plus 72. And we are solving for, again, something in the exponent. So pretty much exactly the same thing that we did to solve for r, we're now doing to solve for t. Alternatively, I could have given you an amount of time. What will the temperature of the water be after 7 hours? And you would just plug that time in for t and then evaluate whatever we have. Either way is fine. I mean, not either way is fine. You could expect to see either, is what I mean. All right, subtracting 72, dividing by negative 40, I get that 1/2 is equal to e to the ln of 4/5. I picked these numbers out very randomly. It is very nice. They are simplifying in this way. That's a nice coincidence. So we get 1/2 equal to e to the ln of 4/5 over 3. Now notice here, this 1/2 isn't because we're working with half-life. We saw this before when we were working with half-life. This is just a coincidence. The difference in temperature by the time I've gone from 32 to 52 is halfway between 32 and 72. So that's why we see this 1/2 showing up here. All right, that distance in temperature has been cut in half. And so again, what's my strategy here for getting at my exponent? What do I have to do? So we could either change the base, and that would work, or we could rewrite as a logarithm, write this as the ln of 1/2. If you prefer changing as a base, I'm not going to stop you. I think that's fantastic. That works as well. This is the ln of 4/5 over 3 times t minus 1. Now, none of you had Algebra 1 with me. If you had Algebra 1 with me, you would have heard me say many, 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 many times that I do not like it. And not that it's like wrong, but that I really don't like it when people distribute automatically. Right? Nothing wrong with taking the ln of 4/5 over 3 and distributing it into those parentheses. But like why would we do that? When if we're solving for t, it's a lot easier to just start by moving that over to the other side. And so again, nothing wrong with distribution. It's just a little unnecessary here. How could I cancel the ln of 4/5 over 3? Well, the ln itself isn't going to cancel, but I want to isolate t here. So what do I have to do with this? Divide it on both sides by it. Now that's going to end up making things look pretty messy. So what's maybe a way that I could do it that's going to make it look cleaner just for the aesthetics? Yeah, multiply by the reciprocal. So instead of dividing by 1/2, I could multiply by 2. Instead of dividing by ln of 4/5 over 3, I am going to instead choose to multiply by 3 over the ln of 4/5. If you did the division, that's fine as well. It just looks a little messy. Although actually I say that, and one of the things that I want you guys to simplify is fraction over, or like thing over thing over thing. I want you to get that into numerator over denominator. So actually you probably would want to simplify this. But if your answer is going to be rounded like this one is, then I guess you don't really need it. We end up with 3 ln of 1/2 over the ln of 4/5 is equal to t minus 1. And so just kind of that last thing that we need to do to solve for t, adding that 1 to both sides, 3 times the ln of 1/2 over the ln of 4/5 plus 1 is equal to t. Where note that this is the amount of time that it took to heat. So this is the amount of heating that actually happened. And then this is the amount of doing nothing. Regardless, either way, we end up with, I get 10.3 hours. What would I have to do if I wanted to convert this into like an o'clock? Like if I set the bowl in a room at 6 o'clock and needed to know the time at which it was, the time at which it hit 52 degrees. What would I need to do at that 0.3? Convert it into minutes. So how would I convert 0.3 into minutes? Multiply by, if I have 3/10 of an hour, how would I convert that into minutes? Multiply by 60? 18 minutes? It was like 10 hours, 18 minutes. Just like if crazy, that ended up being like on a test or something. I don't know. Like a point or two at the very end. All right, questions here with our bell work. So strategy was the same. Solve for R. Use that R to either find a time for a particular temperature or find a temperature for a particular time. I probably would not throw you that weirdness of like the T minus 1. That's more of a bell work idea of like adjusting that input to account for that period in which we are not seeing this kind of temperature change. But yeah, beyond that. How are you feeling? Newton's law of cooling. So, pretty decent. Hopefully, at the very least, the steps are very comprehensible, even if the process itself is long and difficult. It's a difficult problem, difficult styles of problems for sure. Long, 2 pages worth. Although, a fourth of that page is a chemistry lesson, but can't resist. All right, so what is the good news that I promised for today? The good news is that we are going to end off Unit 3 by taking what I consider a pretty serious step down from what 3.4 and 3.5 have been. Now, still, we're going to be talking about exponentials. That is still kind of going to be at the heart of what we are doing. This is really an idea that I would have liked to have introduced earlier when we were talking about lines, In this particular curriculum, because lines were kind of lumped in with what we were doing in Unit 1, it didn't get like its own section like it has in years past. I ended up foregoing talking about this now. So we're just going to talk about it all at once and, kind of see what we end up with. We are going to be talking about sequences and particular types of sequences, and then tomorrow we'll talk about series, or not tomorrow, but Monday, obviously, we'll talk about series. All right. So what is a sequence? There is a very, very classic math definition of a sequence that does a better job of making us very, very confused than it does at actually highlighting what a sequence is. For our purposes, we're going to keep this relatively simple. A sequence is an ordered list of numbers. I guess technically speaking, it doesn't need to be of numbers. The sequences we're going to focus on are, of course, going to have numbers in them. But I suppose you could have just any ordered list, and it would technically be a sequence as well. So maybe we'll just shorten this definition and we'll just say, technically speaking, if we want to be very precise, a sequence is just an ordered list. But really, we are going to be looking at of numbers. But if I gave you a list of bird, car, and plane, sure, that could also be a sequence. Why not? All right. So I want to highlight here the ordered word, because I think the list of numbers is very, very similar to a set of numbers. But the fact that I'm introducing order here is very important. What that means for my sequence is that I can have all the same numbers in my sequence, but I can rearrange them and it will give me a brand new sequence. So for instance, I could have the sequence that is, we'll say 7, we'll say -4, we'll say 10.3, and we'll say 2/3, and so on. Right, so that's one sequence. No rhyme or reason to where these numbers come from. There's no pattern here. And what we will note is that a different sequence can be achieved by just inverting the order of any of our terms. All right, so what we get here might have all of the same elements, but it is a different sequence because the order is different. So we care a lot about the order in which these numbers come. Part of what that order is, part of why sequences are different than just like a set, is the order turns us from a set into actually a function. Right? So thinking here, if I gave you guys this list and your job was to direct me, to map me to the number -4, what instructions would you give me so that I could find -4? Where would I look? Looking at the second, we'll say you're looking at that second sequence there. I'll look at the first term of the sequence. In other words, you might say that f of 1 is equal to -4. If instead of -4, you were trying to direct me to 2/3, what would you tell me? How would you send me to 2/3? Go to f of 4. Look at the fourth term of our sequence. All right, so interesting kind of observation to note here. What are the inputs to this particular function? Yeah, it's the position of the number in the list. This is just where we end up, the position in the list. If I end up at the first position, then that would be an input of 1. If I end up at the 7th position, then that's an input of 7. What are the outputs for this function? Yeah, it's like the stuff that's actually in the list. It's what we find at that position. So pretty clearly here, or maybe not super clear, but if you give it a little bit of thought, I think it becomes very, very clear that every sequence, therefore, must be a function. Because if I give you a list, am I ever going to have numbers that compete for the first spot of the list? I'm never going to have two first numbers in my list. Am I ever going to have two seventh numbers in my list? No, I'm only going to have one unique spot for my numbers in my list. Right? So definitely a function, because you would never say, hey, go to the first spot of the list and then have me be confused as to what I'm looking at. Yeah. The function. Okay, so this is a really, really good point here. What makes sense as terms of what values we should be allowed to plug into this kind of function here? So Haddon's making the observation that it wouldn't make sense to go below 1, and I agree. It wouldn't make sense. In particular, we could use that to like eliminate 0 and also all the negatives. What is the negative first number in our list? That doesn't make sense. Okay. Say again. So, okay, but if we're looking at just like this list here, maybe in like some abstract sense we could figure it out. But if I ask you what f of -1 is for this list, is there any way that we're realistically going to be able to make sense of that? No. We're not going to concern ourselves with it. So mathematically, maybe there's some value to plugging in like negatives, but for the sequence itself, it doesn't really exist. There isn't really anything that comes before that sequence. All right, so negatives don't make sense. To that end, 0 also doesn't really make sense. What other numbers wouldn't really make sense to plug in here? Fractions also wouldn't really make a whole lot of sense. Go to the 3.7th number in this list and tell me what you see. Doesn't make any sense. Can't really make heads or tails of that. And so we would say, what must be true about our domain? What kind of numbers are we allowed to plug in? Positive number that are integers. So those are our natural numbers, counting numbers. This is one of those cases. Remember, we were talking about like reasons we might exclude numbers from our domain. We said, well, we want to be careful about dividing by 0. We want to be careful about taking the square roots of negatives. Actually, we have a couple more rules that we can add. What else do we want to be careful about when it comes to negatives? Taking the square root, but also now thinking like what we've been doing recently. Logarithms of negatives are now going to create issues as well. And then that third rule, which is now, I guess, our fourth rule, if we're adding logarithms as one of this, is going to be arbitrary restrictions on our domain. All right. It doesn't make sense for me to count 22.7 people. That 0.7 doesn't make a lot of sense. We would expect to have like natural numbers there. All right. So again, nothing mathematically about this. It's just like in terms of what our sequence is allowed to do, it doesn't make sense to refer to like the 0.6th number in the sequence. It doesn't make sense to refer to the -7th number in our sequence. And so we'll just stay away from those. Our domain is just going to be the natural numbers. And then the range is just going to be who even knows what. All right. It's just really going to depend on the kind of sequence that we look at. Sometimes the range is like a chunk of the real numbers. Sometimes it's a chunk of the natural numbers. Sometimes it's just completely random and we have no idea. And so we're just not going to really make any kind of statements on the range. The important thing is we're only allowed to plug in whole positive numbers that aren't 0. Range could be anything. So the outputs are just whatever we find there, right? And maybe the outputs are also the natural numbers. We could think of the sequence that is 1, 2, 3, 4, 5, so on and so forth. The range and the domain would match. But you could also have the range be 1, 1, 1, 1, 1, 1, 1, 1, 1, in which case the range is just the number 1. And so it's very varied what you could see like for the range here. And so we're not going to try to make any kind of statement to pin it down. More often than not, when we are talking about sequences, referring to these as like f of 1, f of 4 is fine. It gets the job done, communicates what we need to communicate. More often than not, though, we are going to see this written as what I'm going to call sequence notation. For the people who had questions about what is going on with like a sub n and a sub n minus 1, This is kind of that precursor that might have made that a little bit more clean. Rather than referring to this as f of 1 equals 4, we will often instead say that a sub 1 equals 4. Where the index here just tells us where in our list we live. So a sub 1 tells us that we are first in our list. A sub 7 would be that we are the 7th number in our list. A sub 20, the 20th number in our list. That subscript is like the thing that we are inputting. It's that x value. Right? And it just points us where are we in my sequence. Now, if I want to refer to a generic term in my sequence, or just any random term in my sequence, the way I'm going to do that is with a sub n. So this is just some generic term. All right. I think people generally do okay with a sub n. Again, it's just some random term that I want to talk about. People struggle with a sub n minus 1. So notice here where my minus 1 is. One of the mistakes that I see a lot of people make is they put that minus 1 and they attach it to the a. They like subtract 1 from a sub n, which is not what's going on here. We are reducing the subscript by minus 1. If a sub n is just some random term in my sequence, what is a sub n minus 1? How would we describe this? Yeah, the term that comes before. This is one term before a sub n. What would one term after a sub n be? A sub n plus 1 would be one term after. So importantly here, if a sub n is equal to 6, what can we say about a sub n minus 1? Is it 5? Not a sub 5. Can we say anything about what a sub n minus 1 is? No. We have no idea. That minus 1 is just telling us that we are shifting. We're like here, and then the minus 1 tells us, well, actually, we want to look right here. Right? We just shift our view one spot to the left, or the plus 1 tells us we are shifting our view one spot to the right. All right, questions with our sequences so far? All right. Now, sequences can be exactly what I have written here, which is just a random collection of numbers in a random order. All right, certainly can be. Nothing wrong with that. Fits our definition. It's an ordered list. Is this ordered list particularly interesting for us? I would say not really. And mostly I'm saying that because if I were to ask you to give me a guess as to what a sub 5 is, or a sub 6, or a sub 7, there's no feasible way that you could do that, right? We can't gain new information from what we see here because there's no pattern to what's going on. Right? Maybe you could try and like concoct some kind of pattern, but I made these up on the spot. There shouldn't be a pattern to what is here. It is completely random. And so these kinds of sequences are not ones that are particularly interesting. Now, there are plenty of types of patterns that we could look at for sequences. We're going to focus on two. We're going to be looking at arithmetic sequences and geometric sequences, which each follow a very specific pattern. Does anyone remember what the pattern that I have to follow for an arithmetic sequence is? Yeah, it's just addition. So this is going to be a sequence. And I'm going to be very deliberate in how I define this. This is a sequence with what I'm going to describe as a constant addition pattern. All right. Now notice here, addition pattern could also be a subtraction pattern. If I wanted to subtract 2, how could I accomplish that with addition? Plus -2. So when I say addition, I mean addition or subtraction, but addition and subtraction are just two sides of the same coin, so I'm just going to refer to this as an addition pattern. Likewise, with our geometric sequences, if an arithmetic sequence is a sequence with a constant addition pattern, what would a geometric sequence be? Yeah, a constant multiplication pattern. All right. And in the same way that we can accomplish subtraction by adding some kind of additive inverse, so adding a negative, we can do the exact same thing with multiplication. If I wanted to divide by 2, what could I multiply by? Multiply by 1/2, multiply by the reciprocal of whatever number I'm looking at. And so in the exact same vein, multiplication and division are really just one operation as well. And so I'm just going to label this as a multiplication pattern. But it's like multiplication and or division pattern, which are the same thing. All right. What do I mean when I say a constant multiplication or addition pattern? I can think of some pretty interesting multiplication patterns that would certainly not be like bad and useless like the junk that we see up at the top here. For instance, I could think of a sequence maybe that starts at 2, and then I multiply by 2 to get to 4, and then maybe I multiply by 3 to get to 12, and then maybe I multiply by 4 to get to 48. And what am I going to do next? Multiply by 5 to get to 240, and so on and so forth. So it's not like this is an annoying, useless sequence where I can't derive valuable information from what's going on here. But it's not a constant multiplication pattern because the amount that I'm multiplying by isn't staying the same. So what would a constant multiplication pattern look like? Well, this would be like if I started at 3 and maybe multiplied by 2 to get to 6, and then multiplied again by 2 to get to 12, and then multiplied again by 2 to get to 24. This would be a geometric sequence, and it would go on and on and on forever. Dot, dot, dot. So not that like the first one isn't a multiplication pattern. It certainly is. And it's not that that's not an interesting sequence to talk about. I would say it certainly is. We can ask what is going on at various terms of the sequence, and we can actually make logical deductions about what that's going to be. It's just not geometric. Likewise, we could have weird, and we'll look at an example of this, weird different addition patterns that are perfectly great and really cool, and there's a lot that we can do with those. There just wouldn't be arithmetic. So arithmetic is specifically like +7, +7, +7, +7, +7. Geometric would be like divided by 3, divided by 3, divided by 3, divided by 3. Yes? So the first example would not be geometric because the thing that I am multiplying by is changing. It's changing in a way that we can predict, but it is still changing. Whereas the second one would be geometric because the thing that I am multiplying by is not changing. So this would be not geometric, and this one would be geometric. All right, so let's knock out example 1 here. In this case, we were just trying to figure out whether the given sequences are arithmetic, geometric, or neither. Technically could be both, but we're just going to focus on the arithmetic, geometric, or neither. None of these are both. I want to kind of highlight something. If we limit our view to just the first 2 terms, this is not enough information to make a claim about whether what we're looking at is arithmetic or geometric. If I start at 4 and move from 4 to 2, how could I do that? What are various ways that I could do that? I could subtract by 2, or I could divide by 2, or I could even do what? Like take the square root or something? Maybe it's some weird thing where I'm just taking the square root over and over and over again. Maybe. Who knows? Or like multiply by 0.5. That would also work. Although I would count that under my dividing by 2. And so we need to look at my full picture to really see what's going on. So just looking at the first two terms, not enough. You have to expand your view and say what's going on overall. And when we do that, what do we see as our actual pattern here? We are subtracting by 2, and therefore that this is absolutely right, arithmetic. Likewise for B, if we just focus on those first two terms, 8 and 4, tons of different ways that we could go from 8 to 4. But what do we actually see here as our overall pattern? We are geometric because what are we multiplying by? 1 over 2 or dividing by 2. Either way, either multiplying by 1/2 or dividing by 2. And that tells us that this is geometric. Thank you, Allison. All right, C is a little bit tricky. What's going on with C? How do I move from one term to the next? We're adding x each time, and so what kind of sequence is this going to be? This is arithmetic. All right, what's going on with D? D feels like one of those really, really random ones. Does anyone recognize D here? Okay, so this is a fairly famous sequence. This is the Fibonacci sequence. And in particular, the pattern here is how do I make this 2? Well, I add 1 with 1. How do I make this 3? Well, I add 1 and 2. How do I make this 5? Well, I'm adding 2 and 3. How do I make this 8? Well, I'm adding 3 and 5. How do I make 13? Well, I'm adding 5 and 8. Each term is the sum of the previous two terms. Certainly an addition pattern, but is it a constant addition pattern? No. Is it a constant multiplication pattern? Definitely not. This is an addition pattern. And so this is neither. And then one final one for E. What do we have going on with E here? We are multiplying by -3. How do we know that it's negative? We're like flip-flopping between positive, negative. And so what is this going to be? Geometric. Very good. So nice little step back, hopefully, from all the logarithm stuff that's been floating around. A good little change of pace there to end things off. We are going to finish this up tomorrow, looking at kind of a few other things here. Or not tomorrow, obviously Monday. But until then, 3, 4, 3, 6 classwork due Tuesday of next week. I'll have a study guide probably posted on Monday for the test that we have on Wednesday, and then review day for that test on Tuesday of next week.
Test is Wednesday.
Test is Wednesday.
Arithmetic and geometric follow the same rules,
Except one's addition, one's multiplication.
One's addition.